Welcome once again to Astronomy Daily Live. Hey, everybody. Hope everybody's doing well out there in the universe and on this planet. Thanks to those who are coming in for the live stream. It happens every single day at 2 hours UTC. Now, you're going to have to figure out what that is for your local time. Um, and time is one of those concepts in the science of astronomy that's really, really important. So, yeah, do a little bit of math there and a little bit of thinking to get yourself over that temporal hurdle and see if you can figure out what time it is for you locally, as opposed to you know doing it any other way. Now, the other way, the easy way, which I also um, greatly encourage, is to subscribe and then hit the notification bell. I think it's a bell, and supposedly you will be notified when I go live. So here we are again. The circle of friends is gathering, and you know what? I'm going to get right into it. I'm going to get right into talking astronomy tonight. Hey there, Bobby. I see you in the chat. Hope everything's well. Yeah, everything's okay here. The sun is still. I can still see sunlight. I don't. Yeah, no, you really can't see it from there. Trying to see there. You can still see sunlight coming in through the window. So man, we are a little over a month away from the solstice, and I got to tell you, the solstices and the equinoxes are I've sort of adopted those as my um, holidays. So those are pretty special days for me, and I actually like those a lot more than sort of the man-made holidays, uh, which are I don't know. For me, I guess maybe a little too popular. So I like the solstices and the equinoxes because uh, yeah, those kinds of events, which at least in an astronomical sense, in at least a local um, astronomical sense, are significant and unique and special for the Earth, right? As opposed to one group or the other. The entire Earth goes through a solstice twice a year, um, and an equinox twice a year. So I think that's great. But yeah, it's coming up. But oh, the sun has just set. So see, there's no more bright light on my hand, and I can see on my opposing wall over here that no, the sun is gone. It goes fast, right? I mean, the earth is spinning really fast, really fast. I think probably what I should do at some point, um, I'll try to remember this. uh, hey there, Jill. Hey there, Patrick. Nice to see you in the chat. Is I need to go through that calculation again, uh, to determine how far we actually travel uh, in a 24-hour period, taking into account the rotation of the Earth, the motion of the Earth around the Sun, and the motion of the Sun around the galaxy. And yeah, it's an extraordinary number, and it's sort of a dizzying path. Um, So yeah, I should do that at some point. But yeah, you know what? I think I'm going to get right into the astronomy tonight. And I think what we should do is a constellation of the day. Constellation of the day. Now, the International Astronomical Union, by the way, it is hydrogen hydroxide tonight. Cheers. So, the International Astronomical Union has defined 88 constellations in the entire sky, right? So the northern sky, the southern sky, the whole entire sky, 88 of them. So, let me pull up my live stream on my smartphone, just so I know that that's going. It looks like it is. Yay. Um, So yeah, the International Astronomical Union has defined 88 constellations covering the entire sky, and they've defined their boundaries and all of that as um, yeah, all of that as well. So let's go over to random.org. I'm going to share my screen. As I said, we're going to jump right into astronomy tonight. I'm going to hide that. Already got random.org pulled up, and I'm going to have random.org pick for us a random number between 1 and 88. Now, on my Linux machine over here to my left, I have the list of those 88 constellations in alphabetical order, right? In alphabetical order. So let's have random.org choose a number between 1 and 88, and then I'll look on the list to see which constellation that number corresponds to. All right. And, it's random, so it could be anything, right? And then what we can do is sort of explore that constellation. We can look at uh, the size and the shape and the location, start to look at a few of the stars, look at a few of the non-stellar objects. I'll pull out Burnham's here and see if there's anything interesting there. So, all right, it'll be great fun. Great fun. All right, so let's do it. Drum roll, please. Number three. Number three. Okay, so I'm going to go to my list here, my alphabetized list of constellations, and number three is the constellation Apus, APUS. So I have found in the past that Wikipedia usually has some at least some pretty decent uh, charts showing, sort of showing the constellation, right? And yeah, all right. So let's go in here, and we will find out. Grab the chat again over here, so I don't miss a single hot word. All right, so it's another southern constellation, only visible from the southern hemisphere. So, yeah, what is it about these southern constellations? I think this is like the fourth or fifth one that I've done, and only one of them has been in the north. What I thought this was a random number generator, not a not a southern constellation number generator. So I don't know what's up with that. All right, well, Let's do it. So there it is, and here's the location of the South Pole, the South equatorial pole, right? So there's a lot of ways to sort of get your head around the poles, right? In terms of looking at them. One of the ways that I like to do that is to imagine myself standing on the south pole of the Earth, right? If I was standing on the exact south pole of the Earth, if I look straight up to what's called my zenith, right? 90 degrees from my horizon. What I would be looking at is the south celestial pole, right? So the celestial pole is just an extension of the Earth's pole onto the sky. And at the same time, if I looked at my horizon, right, horizon, and going all the way around, um, that would be the celestial equator, a declination of 0 degrees. By the way, the declination the of the south celestial pole is negative 90 degrees. So it's 90 degrees south of the celestial equator, right? So if you're standing on the South Pole, right, then your horizon is the celestial equator, and you can't see any further than that at all, ever, ever, right? I mean, if you're standing exactly on the South Pole. Now, if you move off of that, right, then you start being able to see over that edge a little bit. Okay, so Apus is over here, really close to the South Pole, right? Like seriously close to the South Pole. Here's negative 60. Here's negative 70. Here's negative 80, right? And then here's, of course, the South Pole itself. So let's see. It's sort of looking like the southern extent of Apus is about what? About negative 82, 83, something like that. It doesn't even look like it's in a straight curve, right? I mean, it looks like it's wider over here than it is over here. So, yeah, well, yeah, and that that's sort of apparent here too. Now, why the International Astronomical Union has done that? Beyond me. Don't have a clue. But it does extend up to what, about negative 67, 68 or so. So you've got 10 and maybe a couple more. So, you know, 14 or 15 degrees that away. And then it extends from what, about 14 hours right ascension, 15, 16, 17, 18, a little past 18 hours declination. And usually how the stars are named are sort of by their visible brightness, right? So alpha is usually the brightest one, beta is the next brightest one, gamma, delta. Oh, my tab just crashed. Why is that? That's a little weird. Um, let's see if it comes back. My chat decided to crash. Oh, I wonder, am I? Let me go over here really quick. Um, it looks like everything crashed, but I'm going to exit that right away. Okay, yeah. All right. So, and then the stars are also numbered. You're really not seeing any numbers here, but the numbers usually start uh, at the most western right ascension, the smallest um, right ascension, and go east. So there aren't any numbers here. We're just seeing, sort of the visible uh, um, stars that have, their Greek letter designations. So I'm going to try to pull up the chat again here. Let's see. Can go there. All right. So, and Wikipedia is showing one globular cluster, NGC 6101, in there as well. So it's not a huge constellation. Um, let's see what else. Let's see what else Wikipedia has to say about it. I'm not gonna. Wikipedia is okay, but I've got what I consider a better source. So, yeah, named by the same guy. 206.3 square degrees. Blah 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 blah. Yeah, there's IC 4499. Okay, so it looks like the Milky Way covers a lot of the constellation's area. Um, so yeah, NGC 6101 and IC 4499. That's kind of cool. That's kind of cool. All right, I'm still going over to pull up my chat again here. Hang with me. Dun, dun, dun. Okay, there's that. I'm going to pause the live stream on my Linux machine. Otherwise, you know what is going to happen. And I'm going to pop out my chat. Okay, now we're good. Now we're good. All right, so what I like to do is, and this this information is probably maybe a little bit more up to date, right? But if we want to dive into the details, we can do that. But what I like to do is I like to go to my 3-volume set called Burnham's Celestial Handbook. And as soon as my picture reappears on the screen, there it goes. I'm going to reach down here and grab volume 1. Grab volume 1. Now the cover of this is really close to coming off. It's being held on by a thread at this point, and it will join the other 2 books in not having a front cover. So Burnham's Celestial Handbook. Sorry, I forgot to hold it up. This is volume 1, 3 volumes, and I don't know if these have been updated over the years or not. I've had these for I want to say like at least 30 years or so. These actual books, um, maybe even a little bit longer. I don't remember exactly when I would have gotten these, but probably when I was like 12 or 13, something like that. And they're organized by constellation, and they just give a lot of really useful information about um, objects, stars, and non-stellar objects in these constellations. So let's go to Apus, which is probably going to be a pretty short, let's see, P comes before Q, because I'm looking at Aquila, Aquarius, there's Apus. Wow, so Apus, maybe we'll have to look at the Wikipedia thing, because uh, Burnham's Celestial Handbook just made me a liar. Well, for most of the constellations, at least, they give descriptions of some of the stars and some of the non-stellar objects. In this case, it's all we get is, and this is typical, right? We get the list of binary stars, known binary stars at the time, and flipping over the page, we get a list of, at least at the time, the known variable stars up here, and a list of the known non-stellar objects. So it looks like there's a couple of galaxies and a couple of globular clusters. And I think those are the two globs that were mentioned in the Wikipedia entry for that. So let's just see. Yeah, the variable stars are all really, really long period. Yeah, many. I think is that days or is that years? I guess that's probably days. Yeah, 119 days, 261 days. Huge variabilities, though, on a lot of these. And at least what this book is saying is that a lot of the periods are irregular, which means they don't have a nice, bright, faint. It does weird things, and that that sort of makes me want to investigate maybe one of these variable stars, one of these irregularly, don't really know what the period is, and we can actually look at a pretty bright one. R, a star named R in the constellation of Apus, at least according to Burnham's here, has a magnitude variation between 5.0 and 6.3, and has one of those irregular periods. So let's see if Wikipedia says anything at all. But what I probably really want to do is go on to Simbad and see if there's anything interesting there. But while we're interneting, we can do a quick look and see if there's any mention of R here. Alpha, Zeta, Beta, Delta. Delta's a double star. That's cool. Theta. So two star systems have exoplanets discovered by Doppler spectroscopy. That's kind of cool. So they're talking about S-Opus, talking about N-O-Opus. I don't see R-Opus mentioned anywhere here. Oh, there it is at the end. R-Opus is a star that was given a variable star designation, yet has turned out not to be variable. Well, that's kind of interesting. So back when Burnham's was published, I guess it was thought to be a variable star, and it turns out that it does not. It is not a variable star. Let's look at it anyway with Sinbad. Let's see if Sinbad has anything interesting to say about R. Opatus. Whoop! I was going to start typing Opatus. I want to do Sinbad. Keep my chat handy here. I've got two of them. Oh, now I've got two of them running. All right, there we go. Bobby, the webcam that I am using right now is literally a $5 webcam. It the the intention was never ever to use this for what I'm using it for at all. At the time, I needed to be able to Skype, and so it's like just grab something fast and cheap, right? And and so when I decided to do this live stream, it's like, oh, okay, well, I need a webcam of some sort. What have I got? Oh, I've got that one. So yeah, I think I I'm sort of seeing relatively soon. I hope a small improvement to the webcam, at least. I think right now I am actually um, doing this in 780, right? 780, is that the right designation? Um, and yeah, there there are weird technical things. Probably a combination of the hardware that I'm using, which is just a laptop and it's an old one, and my bandwidth, which is very low, right? Low enough that at least at the moment I'm sort of stuck having to use Google Hangouts. I would love to switch to OBS, but my hardware and my bandwidth just isn't going to um, handle it. 720p. Yeah. So I mean, uh, that's acceptable. Uh, I think. I mean, I look at these two. I don't really watch them, but I look at a few of them, and I mean, it's acceptable. It definitely isn't great, um, but if I guess if the quality of the video and the audio are more important than the quality of the content, well, yeah, I mean, sorry about that, but that's how it goes. Hopefully, the content isn't as poor. So, um, all right. So let's look at R. Opatus and see if there's anything at all in Simbad. So it's calling it HD 131009. Is that also R. Opatus? I don't know. 1457. 7628. 7639. How can I confirm that this is R. Opatus? So I'm not seeing it. Oh, there it is. There it is. And interestingly enough, well, yeah, that says V star. I don't know if that means variable star. All right. So apparently this is R. Opatus. R. Opatus. And they're calling it a high proper motion star, which just means that you know, it um, as as time goes by, its its motion across the sky is just very, very high. So probably meaning that it's either relatively close to us, and or it's moving really, really fast. So yeah, there are the celestial coordinates there: 14 hours, 57 minutes, 52.98 seconds, and a declination of negative 76 degrees, 39 minutes, 45.55 seconds. So yeah, it's got a bunch of names. Looks like it's coming towards us at a velocity of 31.2 kilometers per second. And I believe that when it says, yeah, parallax is a way of working out how far away it is. So yeah, we're not going to get into that tonight. Um, it's a pretty red star. Do you see how bright it is in J, H, and K? Those are, you know, red and infrared um, filters, much um, much brighter than in sort of the visible bands. And you can see, you know, the picture over here, which I guess you would call sort of a true color picture, is indeed, you know, red looking, orangish looking. So that's cool. Got a bunch of different names. Uncle Bill's been kind enough to put a few of those on the chat, but it's, I mean, it's got, wow, it's got 15, 20 different names, right? At at least. And it you know, I mean, look, it's still, it's it's an AAVSO object. AAVSO uh, is that the American astronomical, or um, the American the American Association of Variable Star Observers. I think the first A is American. So a bunch of different names. Some of them correspond to, you know, the right ascension and declination. Most of them don't. Most of them don't. And these are just different catalogs, right? A couple of references, so that might be interesting to dive into a little bit. Lots of measurements here. So pretty consistent radial velocity, um, and it being negative means that we and it are moving towards one another at pretty good clip, you know, 31.2 kilometers per second. That's a pretty good clip. Um, okay, so here's the proper motion in right ascension and declination. So this, I would think, would be like in arc seconds per year. So wow, it's moving like over an arc minute per year in negative RA. So it's moving towards the west, and it's moving south, right? So that's pretty good. Let's um let's do some simple calculating here. 68.69 squared plus 15.71. Whoop, 15.71 squared, and then the square root of that. So that's about 70 arc seconds per year actual motion or so. So yeah, that's over 1 arc minute per year, and that is fast. That's very, very fast. Cool. Let's go back and look at these references here, see if there's anything incredibly interesting. Thanks, Uncle Bill, for the link to my Discord too. Make sure to join that if you haven't already. That's where a lot of conversations can continue, and I try to post things there, and it's you know, sort of a free for all of sorts. You know, post what you like. We've got music up there. We've got visual art. I post links to papers. If I find anything really, really cool, I've got a channel over there that's called Links to Awesome. That you know, are just awesome things. Multiplicity, binary stars. Catalog of multiplicity among bright stellar systems. Basic physical parameters of a selected sample of evolved stars. It looks like a pretty basic paper there. Let's take a look. Let's go down to the, hopefully there's an actual paper that we can grab. Yay. All right, cool. Let's take a look. Now, theoretically, our Apus is going to be one of these stars that have been sampled here. So let's look for that first, and then we can maybe go dive into the paper a little bit. I want to look for a list. Higher star sample. Let's see. What is it? 131109. Let's look for 131109. Let's go all the way up to the top again, because it looks like they're listing them as HD numbers. So 131109. Here it is. So effective temperature, 4,158 degrees, probably Kelvin. Log G is the measure of the gravity, probably based on the gravity of the sun. So it looks like it's a little bit higher than the sun. Don't know what these other values are. Let's see. HD number, effective temperature, iron content, spectroscopic gravity, and microturbulence. Huh. Don't know about microturbulence either. But all right, so there's at least one reference to it. Let's see if there's another one. I think there is. What's this one? Stellar parameters is derived from the observed, probably absolute magnitude, effective temperature, and metallicity. So that's pretty bright. See, absolute magnitude is the is the uh, is the apparent magnitude of an object if it were to be 10 parsecs away from us. So if this star were 10 parsecs away, then it would appear as a negative 0.22 magnitude star. Okay, so just for comparison, our sun, if it were placed 10 parsecs away, that's 32.6 light years away, it it would appear about magnitude, I think like 5.2, 5.3 or so. So this star, our um, Apus, is much brighter than the sun, much brighter, significantly brighter. That's pretty cool. Doesn't look like it really says anything else. HR diagram showing effective temperature versus luminosity. So that's sort of, the intrinsic brightness. Don't know which star is which. Don't have them marked here. All right. Well, sort of interesting. Sort of interesting. Let's go back to the Wikipedia. See if there's anything else. Why don't we take a look at NGC 6101 and let's see if the HST ever imaged that. So let's go over to the HST archive. Oh, archive. And let's see if we can find some HST images of, what was it again? 6101 NGC 6101. H. Oh yeah, quite a few. With the Wild Field Camera 3, so that means we're actually getting image data. So yeah, let's take a look. Don't see anything too interesting there. That's kind of weird looking. But this is what astronomical data looks like, right? I mean, it's got weird stuff in it that you have to take into account sometimes. That's a little strange. Let's see what else we got here. Um, different data set, different different date. Oh, okay. I don't know if we're looking inside the cluster or what exactly. Yes, we are looking inside the cluster. Oh, All right. Well, now I'm really curious. Let's go over to Simbad and look at it over here. 101, right? Oh, uh, hip. I think that I'm not exactly sure which catalog that is. Um, let's we might be able to easily find out. Probably Hipparchus. I'm guessing that it's probably the um, um, Hipparchus uh, star catalog. That's my guess. That's my guess. I will try to investigate that further. All right, so let's use. Can we use SDSS? Is the Sloan Digital Sky Survey? Is that? No, we're not going to be able to use that because it's too far south. Well, it doesn't look like it's an incredibly loose globular cluster. I mean, there's lots of stars there. Huh. So yeah, for some reason, the stars in this cluster are just not popping out at all. There sure is a lot of them. But yeah, I'm just not seeing much of anything unless all of these stars are associated with that cluster, which is, I suppose it's possible. Don't know. Let's look around a little bit more and go way back in time. That's more like what I would sort of expect to see in a globular cluster. Pretty cool. Lots of stars for sure. Makes me dizzy. All right. Well, I think I'm going to cut this one short tonight. Let you guys go a little bit earlier than normal. So let me stop sharing here and say that I will see you again tomorrow in just a little bit more than 23 hours from now. And yeah, we'll do something else astronomical. You know, the circle of friends will be created again, and we'll come in here with our virtual lounge chairs and sit around and think and talk astronomy for a while. Um, turn off the TV, forget about the news, and think about the rest of the universe instead, just for a while, right? We can come back to Earth right after this. So, all right, take care, everybody. I will see you on the spin tomorrow. Peace, cheers, and all that. All right, take care. Bye.